Okay, so in the last lecture we were discussing the Noether's theorem, which basically states that whenever we have a continuous symmetry under which the theory is invariant, you have a corresponding conserved quantity. And as an example, we saw that if the theory is invariant under a global symmetry, so phi goes to phi plus delta phi, then you see that delta L is equal to 0, and this implies del mu j mu equal to 0, where j mu is del L over del mu phi delta phi, right. This is what we have seen in the last lecture. If you have, in addition to this, so if you consider more general symmetry transformation, where the field phi of x goes to phi prime of x prime and the coordinate x goes to x prime, which is x plus delta x, then you have to be a bit more careful. What you need to consider in this case is the invariance of the action, and the invariance of the action under such a transformation basically implies that this quantity is equal to 0. Delta L plus del mu of L del x mu. Okay. So, to see why the invariance of the action leads to a condition like this, let us consider a simpler one dimensional case. Okay. So, consider this integration in one dimension from the interval a to b f of x dx. Let us make a transformation, coordinate transformation, x goes to x plus delta x, and let us assume that under such a transformation the function f of x goes to f prime of x prime, which is again f of x plus delta x and so on. So, under such a transformation, this integral will transfer to f prime of x prime dx prime, and the interval now actually the integration limits are now from a prime to b prime. If this quantity is invariant under such a transformation, then this difference is to be equal to 0. So, the invariance implies a prime to b prime f prime of x prime dx prime minus integration a to b f of x dx is equal to 0. Now, since we are considering infinitesimal transformation, here this a prime will differ from a by an infinitesimal amount, so is the quantity b prime. So, this integration is actually a plus delta a, and here again the integration limit goes from a plus delta a to b plus delta b. Now, you can do even better. In this integration, this x prime is just a dummy variable, you can change this to x. So, what you get is a plus delta a, b plus delta b, f prime of x dx minus a to b f of x dx. So, f prime of x is nothing but f of x plus delta f. So, we will substitute it here, then this is equal to a plus delta a, b plus delta b, right. Now, what is this quantity, this difference here? You can see that this difference is nothing but f of b delta b minus f of a delta a. So, what you get is, if you require this quantity to be invariant under such a transformation, then you see that integration delta f plus d over dx f of x delta x integrated from a to b is equal to 0. If you consider quantities up to first order in variation, then this is the quantity which is equal to 0. So, you can do a similar analysis in 4 dimensions, and then the invariance of the action under the symmetry transformation phi of x goes to phi prime of x prime, which is equal to phi of x plus delta tilde phi, where delta tilde phi is phi prime of x prime minus phi of x, whereas delta of phi is equal to phi prime of x minus phi of x is given by this condition d4x delta L plus del mu times L delta x mu is equal to 0. Delta L is what we have derived in the last lecture, and what we saw is delta L is equal to del mu of del L over del mu phi delta phi. However, we want to express this quantity inside the curly bracket in terms of the quantity in terms of the transformed quantities delta tilde phi and delta x. So, let us express everything in terms of delta tilde phi. We have already derived in the last lecture delta tilde phi is equal to delta phi minus del phi over del x mu delta x mu, right. So, we will substitute, I am sorry, there is a plus, we will substitute for delta phi here. Delta phi is delta tilde phi minus del phi over del x mu delta x mu. We will substitute it here and we will put it in this expression, then we will get a conservation law. So, let us do that. When we do that, we get d4x del mu of del L over del mu phi delta tilde of phi minus del phi over del x nu delta x nu plus del mu of L delta x mu Now, since these variations are arbitrary infinitesimal variation, the integrand has to be equal to 0, and hence what we get is, we get again a conservation law, which is del mu j mu equal to 0, where the conserved quantity j mu is given by del L over del mu phi delta tilde phi minus del L over del mu phi del mu phi delta x nu plus L delta x mu. This is the most general conserved current for the transformation under consideration. We can rewrite this quantity as follows. This can be rewritten as del L over del mu phi delta tilde phi minus T mu nu delta x nu, where the quantity T mu nu is defined to be del L over del mu phi minus L delta mu nu. We will see what is the physical interpretation of this quantity in a moment. For that, let us consider a transformation for which delta tilde phi equal to 0 and delta x nu is simply some translation a nu. So, we will consider the symmetry transformation to be translational invariance. If the theory is translational invariant, if we have translational invariance, then we have delta tilde phi equal to 0 and delta x mu is some infinitesimal parameter which I will call as a mu. For this transformation, our conserved current J mu is equal to minus T mu nu a nu, or the conservation law is simply del mu J mu equal to 0 simply implies del mu T mu nu equal to 0. This is what we get. So, the conserved charge, instead of getting a single conserved charge, because you have a free index nu, we get a set of 4 conserved charges here. The conserved charges are d cube x d 0 nu. This I will define to be p nu. Let us see p 0, the 0th component of the conserved charge. P 0 is basically d cube x t 0 0. What is t 0 0? If we look at the expression for t mu nu, then this is nothing but d cube x del L over del 0 phi del 0 phi minus L. What is this quantity? This is the Hamiltonian density and this is integrated over the entire space. So, P0 is the Hamiltonian H, and Pi, the ith components are basically d cube x P0 I. So, this is nothing but d cube x del L over del 0 phi del I phi. So, this is the momentum contained, this is the total momentum contained in the field configuration, and this is the total energy. So, this is the reason this quantity T mu nu is known as the energy momentum tensor, and what translational invariance implies is the conservation of the energy momentum tensor. So, the conservation of energy momentum tensor is actually a consequence of translational invariance. Now, we can consider Lorentz transformation, invariance under Lorentz transformation. So, let us again consider the conserved current J mu, which is del L over del mu phi delta tilde phi minus T mu nu delta x nu. When we make a Lorentz transformation, delta x mu basically becomes epsilon mu nu x nu, all right. And the fields usually transform non-trivially under Lorentz transformation, depending on what kind of field we are considering, we have some transformation. So, the field transformation delta tilde of phi, I will write it as half epsilon mu nu s mu nu phi. In general, this phi will also carry some index. If it is a vector, it will carry one index mu. If it is spinor, it will carry spinor indices. If it is a tensor, it will carry different index, and so on. And accordingly, we have some transformation law, which I am writing in a compact way like this. So, this is how the field transforms, and this is the transformation of the coordinate. We will substitute this transformation here, and then what we get is J mu is equal to del L over del mu phi times half epsilon alpha beta s alpha beta phi minus T mu nu epsilon nu beta x beta. Okay. I can raise this index nu here and lower the index nu in this place, and then since this is a dummy variable, I can change this nu to alpha. When I do that, what I get is half epsilon alpha beta del L over del mu phi s alpha beta phi, and here minus epsilon alpha beta T of mu alpha x beta. The second term here, I can rewrite this as half epsilon alpha beta del L over del mu phi s alpha beta phi minus epsilon alpha beta with a factor of half T mu alpha x beta minus T mu beta x alpha. Now, since epsilon alpha betas are arbitrary infinitesimal quantity. So, what we get is actually a conserved quantity which I can denote as m mu alpha beta, and del mu j mu equal to 0 implies del mu of epsilon alpha beta m mu alpha beta equal to 0. Since epsilon alpha beta are arbitrary infinitesimal quantities, so this simply implies del mu m mu alpha beta equal to 0. So, what we get is actually a set of 6 conserved quantities which are denoted by m0 alpha beta, which is d cube x m mu alpha beta. These are the quantities which are conserved as a consequence of Lorentz invariance. What is m mu alpha beta? M mu alpha beta is given by half del L over del mu phi S alpha beta phi minus T mu alpha x beta minus T mu beta x alpha. Now, what is the physical interpretation for this quantity? If you look at m0 alpha beta, look at the second term of m0 alpha beta. The second term basically is T0 alpha x beta minus T0 beta x alpha. If you consider the ijth component of m0 alpha beta, then you get T0I xj minus T0j xi, which is basically the ijth component of the orbital angular momentum. So, the second term here is the orbital angular momentum, and hence this first term here must be the intrinsic angular momentum of the field. So, this is the intrinsic spin and this is the orbital angular momentum. So, as a consequence of Lorentz invariance, the sum of the intrinsic angular momentum and the orbital angular momentum remains conserved. And you can see the spin of a field is determined by how the field transforms under Lorentz transformation. If the field does not transform under Lorentz transformation, if you consider a field which is scalar under Lorentz transformation, then obviously the first term here is 0 and hence it has no intrinsic spin. That is why the scalar quantities, the quantities which are scalar under Lorentz transformation have spin 0, and whether you have a spin 1 or spin half field etc. are determined by how the field transforms under Lorentz transformation. This is the term which basically defines what the spin of the field is, and the sum of the spin and orbital part is conserved. Okay, so what we have seen, what we have discussed so far is we discussed classical field theory, we derived the Euler-Lagrange equation, and then we considered theories which are invariant under continuous symmetries and their consequences. Now, we will discuss how to quantize a given classical theory. So, how do we carry out quantization of a classical field? We will consider the usual non-relativistic quantum mechanics. You have x of t and xi and pj of t, these are operators in the Heisenberg picture, and then all of us know the fundamental relation that the commutation of xi and pj is I delta ij. We will take this fundamental relation in non-relativistic quantum mechanics, and then we will discuss the generalization of this to quantum field theory. An obvious guess to generalize is that this x, the analogous of x is the field phi of x t, and the conjugate momentum is the conjugate variable pi of x t. Only thing is that there are discrete levels here I and j, but here you have continuous parameters parameterizing these fields phi of x, a set of 3 continuous parameters. So, what we do is we will start with a commutation relation which looks like phi of x t, pi of y t. Since x and y are continuous variables, so instead of Kronecker delta you have the Dirac delta. This is given by I delta of x minus y, where delta of x minus y is the Dirac delta function, 3-dimensional Dirac delta function. Which has the property that integration delta of x d cube x equal to 1 and delta of x minus y f of x d cube x is f of y. All of you are familiar with the Dirac delta function. So, we will assume the fields phi of x t and pi of x t to be operators, and then we will start with this commutation relation, and then we will quantize the theory. What is the commutation relation between phi's and the field phi of x t and phi of y t, and the other commutation relations phi of x t, phi of y t, commutator of phi of x t and phi of y t is equal to 0, just as in quantum mechanics x I x j is equal to 0. Analogous relation in quantum field theory is 2 phi's commute, and so are 2 pi's, pi of x t, pi of y t is equal to 0. So, let us start with these basic commutation relations and then see what we get. So, we will consider a very simple example, an example of a Klein-Gordon field. And quantize it. So, the Lagrangian for a Klein-Gordon field, which is a real scalar field of mass m, is given by half del mu phi minus half m square phi square. We will start this system and then we will quantize it. So, let us look at the equation of motion. The Euler-Lagrange equation is del L over del phi minus del mu del L over del mu phi is equal to 0. The second term here, del L over del mu phi is basically del mu phi, and del L over del phi is minus m square phi. When I substitute this, what I get is del mu phi plus m square phi equal to 0. What is the Hamiltonian of the system? The Hamiltonian is integration d cube x times the Hamiltonian density h, which is so the Hamiltonian is just del L over del 0 phi times phi dot minus L. We can evaluate this, it is very straightforward. You can see that del L over del 0 phi is basically phi dot. So, the quantity inside the bracket is phi dot square, the Hamiltonian density H is phi dot square minus L, and this will give us half phi dot square plus half grade phi dot grade phi plus half m square phi square, and the Hamiltonian of the system is just H is integration of this over the entire space. Now, we have to take these phi's, all these quantities inside the bracket to be operators. The question is, given such a system, how can you find the spectrum? What are the eigenvalues, eigenstates, and so on. The way usually we find is, if we can write this Hamiltonian to be a sum of normal modes, then we know how to find the spectrum for such a system. So, we will do that. To do that, you know, the equation of motion actually admits plane wave solutions, which are of this form, phi of x t goes like e to the power minus I k dot x, where k dot x is k mu x mu, and this becomes a solution of the equations of motion, provided omega, which is defined to be k 0 equal to square root k square plus m square. If k 0 is equal to this, then this satisfies the equation of motion. So, this is the plane wave solution of Klein-Gordon equation. A general solution, most general solution will be superposition of solutions like this. So, more generally phi of x t will be given by d cube k over 2 pi cube 2 omega times a k e to the power minus I k dot x. Since the field phi is real, we have to also add the complex conjugate of this quantity here, which is a dagger k e to the power I k dot x. Here note that this factor 2 omega is just for convenience. We will see later that if we take this, then the integration measure is Lorentz invariant. So, if this is phi, what is the conjugate momentum? Pi of x t is basically del L over del 0 phi, which is del 0 phi, and from this expression we get this to be d cube x over 2 pi cube 2 omega times minus I omega a k e to the power minus I k dot x minus a dagger k e to the power I k dot x. What we will do now is we will take the fundamental commutation relation, which is phi of x t pi of y t equal to I delta of x minus y, and then we will see if this is the commutation relation between phi and its conjugate momentum, then what is the commutation relation between these operators a k and their Hermitian conjugate a dagger k. To derive these commutation relations, what we need to do is we can invert this relation, and then we can write A's a k and a dagger k in terms of the fields pi of x t and phi of x t. So, we will invert this relation, and then we will derive the commutation relations a of k, a dagger of k prime, and what is the commutation between a k prime, and so on. All right. So, this is what we will do. So, let us look at the expression for phi, and from this relation what we can do is we can consider integration d cube x e to the power I k prime dot x times phi of x t. So, this is going to be integration d cube x. When we use this solution here, then integration d cube k over 2 pi cube 2 omega times a k e to the power I k prime minus k dot x, and here plus a dagger k e to the power I k prime plus k dot x. Okay. Now, look at this. Here, because k prime minus k dot x has two terms, which is omega prime minus omega times t minus the 3 vector k prime minus k dot x. So, this will give two terms, and when we carry out this integration over d cube x, we will get a delta function. We will use this relation integration d cube x divided by 2 pi cube e to the power minus I k prime minus k dot x. This is the Dirac delta function, delta of k prime minus k. So, the first term here will give you one delta function, and the second term here will give you another delta function. In addition, there will be a factor omega prime minus omega e to the power I omega prime minus omega t here, and e to the power I omega prime plus omega t in the second term. So, when I use this relation here, what I get is d cube x e to the power I k prime dot x phi of x t is equal to integration d cube k divided by 2 omega in the first term a of k e to the power I omega prime minus omega t delta of k prime minus k, and in the second term I have a dagger k e to the power I omega prime plus omega t delta of k prime plus k. Okay. Now, you can carry out the k integration, and when you carry out the k integration, you see here omega prime, if k prime is equal to k, then omega prime is equal to omega. So, this exponential factor here will become 1, whereas in the second term you will get e to the power 2I omega t. So, when you carry out this integration, what you get is integration d cube x e to the power I k prime dot x phi of x is equal to 1 over 2 omega a of k prime plus a dagger of minus k prime, because as you can see here you have delta of k prime plus k. So, when you carry out the integration over k, here you have to substitute k prime by minus k, which is what we have done here, and then e to the power 2I omega prime t. Now, there is no reason to keep k prime here. So, what I will do is I will denote this prime, I will delete the prime here. So, there is no prime in this expression. All right. You can do a similar analysis, and you can consider d cube x e to the power I k dot x pi of x here instead of phi, and I will leave it as a homework for you. What you will get by doing such an exercise is minus I by 2 a k plus I by 2 e to the power 2I omega t a dagger of minus k. Now it is very easy to write A and its Hermitian conjugate A dagger in terms of the fields phi of x and pi of x. So, this basically implies A of k to be integration d cube x e to the power I k dot x times I pi x plus omega phi of x, and A dagger k is equal to d cube x e to the power minus I k dot x minus I pi x plus omega phi of x. So, what we will do in the next lecture is we will consider these two expressions for A and its Hermitian conjugate, and then we will find what are the commutation relations using the fundamental commutation relations between phi and pi. All right.